So Frédérick, he's an HPC specialist and operation team leader at Universite Laval.
Yep.
Advanced Computing Center. He's also a regular contributor to Compute Canada's and Calcul Quebec's projects and ongoing operations. We're really glad to have you here, and I'm looking forward to your talk. Thank you.
Thanks for coming this way. So I'm Frédérick Lefebvre. So I work at Laval University, and I'm going to be sharing with you today our experience in monitoring an heterogeneous lustre environment, more specifically our experience in dealing with different lustre versions and different software stack. So I'm going to go a bit over our site description and what we do, so that you get a bit of context about us, and then our history with monitoring and what we're doing right now. So you'll see that you're going to see a lot of the concepts that have been introduced in the past 2 hours. So obviously we've approached similar issues in a similar way, but with different tools. And at the end, I'll finish with our plans for where we want to take this thing. So I work at the Advanced Computing Center at Laval University. We are part of Calcul Quebec and Compute Canada, which you may know about. Our main mandate is offering computing cycles and storage for academic researchers in Canada. So access is free for any academic researchers. And we also have paid for access for commercial users. We currently operate 2 clusters and 4 lustre file systems at our sites. And we've been in operation since 2010, 2009. So our current infrastructure, so you get we're not a big site, so we have a little bit over 1,000 lustre clients when things go well. Client versions go from 2.16 to 2.5.3, and I believe we still have a couple of 2.4 clients running around. And we have 2 InfiniBand fabrics and 6 Elnet routers bridging the two. We're currently operating 4 lustre file systems. So you see we have a bunch of different versions and different hardware generation in there. So we have a 500 terabyte lustre file systems running lustre 2.5.3 with ZFS. That's 16 OSSs and 16 ZFS target. That is our Scratch file system. So this is the one from which we expect good performances. We have our own directories and our project space on a second 500 terabyte file systems running an antiquated 2.16 lustre version. This one has 6 OSSs and 36 targets. And we have a more recent cluster store CS6000 with a 1.4 petabyte file system running Seagate's lustre 2.10, and its little brother CS3000. 120 terabyte with lustre 2.10. Again, this one has only 2 OSSs. So our basic infrastructure, basically all of our lustre file systems are connected to the same IB fabric as our main cluster. And we have a more recent, smaller GPU cluster that has its own IB fabric, and that came with 6 Elnet routers that are used for connectivity to the lustre file systems. So we've been running lustre since 2009. We bought our first systems from Sun Microsystem in early 2009. And in the beginning, we didn't know much about what we were doing with this parallel file system thing. So we just monitored for the sake of it. And we initially wanted to, only figure out drive failures and server failures. Over the years, we played with a lot of options to monitor these things. We used CollectTL for a while and LMT with Cerebro for a good while also. In the end, we converged toward using Ganglia with custom geometric scripts for lustre and monitoring IB. That worked fairly well. So the Ganglia interface was doing most of the things that we needed it to do for that at the time. What we realized down the road is that, well, our own home-grown script were kind of inconsistent quality, and they tended to use a lot of resources on the servers on which they were running. So if we were running Lustre monitoring every 30 seconds or so, we will see the monitoring script come up in the process list pretty high as far as memory and CPU usage was concerned. What we realized also is that we were, at the same time, we were monitoring a lot of other information about our data center, like physical infrastructure, the power usage, cooling, and stuff like that. And we're beginning to monitor job usage for the end users. And by having the performance, Lustre performance data into Ganglia, we were kind of isolating it away from the rest of the data from which we needed to cross-reference it with. So when we realized we needed something else, we sat down and our users keep, and even the staff keep asking the same questions about our Lustre file system. So, why is it so long? Navigating or traversing the file system. Why is checkpointing taking so long? Or, just basically, what file system should I use? Or why is the logging node so slow at that given point in time? And we figured we had all the information required to answer those questions, but it was dispersed across multiple systems. And most of the time, if a user support specialist, came forth with a question like that from one of the users, he needed to find one of our file system experts who knew the special magical formula to get all of the information, out of Ganglia and the logs and the /proc on Lustre to be able to get a straight answer. So we had data almost everywhere. So for a couple of years, we've been collecting performance data about jobs in a MongoDB database. At the same time, we had all the Lustre performance data from every client in the system and every server in the Ganglia, so RRD files. And we had the scheduler data that we wanted to cross-reference with that in log files on the systems. So it's easy to picture this whole spider web of custom scripts, when's the time to generate a report for end users or even for staff. So we set a couple of requirements for a new monitoring systems that we wanted to deploy. So basically, our first priority was to give staff as close to possible near real-time view of the file system utilizations and load, and basically the status of all the OSTs and the general file systems. And down the road, we would like to be able to provide end users with the data required to be able to qualify and characterize their IO patterns for their jobs in the perfect world, or that they can get some help from one of our analysts. And if we weren't able to cross-reference, that information with the scheduler statistics, that will count for, bonus points. And our last requirement is that we believe in keeping all of the historical data. So we've been trying to keep everything since the beginning of times in our data center. And we believe that with the amount of storage that's available to us today, it doesn't make sense to lose granularity with our RRD files. So we wanted a system in which we will be able to go back in time 6 months or a year down the road and be able to compare two jobs running on different versions of Lustre or different file systems, or just after an upgrade to the same file systems. And we believe that information is also useful when sizing new systems that we could purchase in the future. So enter Splunk. So I'll assume that almost everybody is familiar with what Splunk is. So we've been using it for a couple of years, mostly to aggregate our log files on the systems and do simple research and statistics on errors and events. And we've done a lot of work with it also to get information out of our InfiniBand Fabric error logs and the logs of our OpenSM servers. So we know it's well suited to indexing a lot of unstructured data. So we figured, well, let's see how much stuff we can push into it and how it goes with it. So what we figured basically is that if we can simplify our monitoring data to key values, and we should be able to just push it into Splunk and use Splunk as the graphical interface to query the performance data. So our plan was to collect performance data from Lustre / proc file systems on all the Lustre clients and Lustre servers in our infrastructure. And just because we don't have that many resources, and it makes us lazy. So instead of using complicated sockets or anything else, we'll just send it through syslog so that it naturally makes its way to our Splunk server. The log will then be indexed to be visualized in Splunk. And so we decided to use separate index for the performance data into Splunk, just to be able to speed up the query a bit. And we assume that we will have to make heavy use of the Splunk data model acceleration to make the queries in a reasonable time. So we looked at different options for data collection, and by default we don't like to reinvent the wheel. But we figure out, similar to other talks earlier, that most of the existing tools to monitor Lustre are tied to a single or a specific backend for storage. And that's most of the time it's either round-robin database or it's a relational database. And so since our needs were much simpler, all we wanted is the data and just be able to write it down. So we decided to write our own tool to collect the data while still trying to minimize the work and code writing. So what we did in the end is we wrote a pretty simple application. We called it CQMon. It's just a basic daemon that we run on each of the nodes, and it just iterates. Basically, in time, runs a set of plugins that use, hopefully, when possible, existing libraries to gather the information on each of the nodes. It uses syslog to log the information to the system logger, which is pushed by our syslog to the Splunk server, where it's indexed into the NoSQL database that sits under Splunk, and made available for query and visualization. So basically, we wrote the whole thing in Python because we wanted to make it be quick about it. We have a configuration file which specifies which plugin that we want to run on which machines. And so each plugin is run at a given interval and logs the result as key values to syslogs. And we don't log zeros. So when doing queries down the road, we assume that the absence of data is a zero, basically. The only change that we've made the configuration of the local machines to make the thing more manageable is we added syslog filters to all the machines to separate the performance logs from the system logs, so as to make sure that if we have to go on a machine to check a sample of system logs, we don't have to deal with all that stuff that comes every couple of seconds from the monitoring. And to go with it, we wrote a pretty simple Python library we called Lustre Utils. We're hoping to make it into a library to interact with Lustre through the /proc file systems. Basically, what it does to these days, it has a couple of simple objects to load stats for different components of the Lustre file systems, and make them available through an object model associated to the given component. So the way it works into a bit of more detail. So we have CQMon, which reads a configuration file, which is managed through Puppet on each of the machines. The configuration file defines the intervals for the test and the list of tests that we want to run on each machines. In the case of Lustre, so we have, for example, on an OSS server, we have the CQMon Lustre OSS test, or a plugin that is loaded, which will instantiate through the Lustre util library, Lustre OSS objects, which is used to read the different /proc stats for OSS servers and OST servers and load them into the appropriate object, which are made available to then to Seqmon to just print out as key values to syslog. And for most of the other aspect of monitoring, we've used Python PSUtil, which is a common library available in most places to monitor the OS level stats and IO stats for the local drives on the machines. That part was important for us because, as you've noticed, we have some homegrown Lustre file systems, but we also have two Seagate cluster store file systems, which have a very limited Linux operating system running on them. So since we wanted to run that daemon on the cluster store stuff, also we needed to minimize the number of software dependencies than we had to install on those machines, so as not to get into trouble with Seagate support. So the state of the thing now, obviously it's a work in progress. We've tested it only on our own system, but it still goes from 216 to 225x with and without ZFS. We've made the Python library available through the Calcul Quebec GitHub, and we're hoping to add the Seqmon part to there also. I don't think it's something that can be taken as is and used by anybody else, but it's interesting to share code, and maybe it can inspire ideas in somebody else. And right now we offer the basic stats, for the MDS, OSS, MDT, OST, and all the required stats for the clients. The difference between presented earlier are doing is that we grab the client stats from the compute nodes themselves. We thought that was a mistake, when we did it. We would have preferred to do it on the server. We had the misconception at the time that it will be more difficult to do it on the server side. It turned out that everything is available on the server, and we probably change it down the road. But it's kind of a benefit also, though, because it makes it much easier to map performance data with the jobs running on the individual compute nodes. And so that's it for data collection. It's that simple, and we didn't develop anything as far as UI is concerned to visualize the information. We used basic Splunk dashboards that we've put together. The most interesting one that we're working with is we wanted a dashboard to give a single overview of all the file systems independent of their versions to see what's the state of our infrastructure right now. And one specific dashboard for each file systems to deep dive in more details. And we also developed one pretty interesting for job reports, so to cross-reference Lustre performance data with jobs running on the scheduler. So obviously, some of those reports, especially if we take them across too big of a period of time, takes quite a while to generate. So we tend to only look at them for a short amount of time, like a week or a couple of weeks of time. But it still preserves the abilities to go back in time 6 months or a year, if needs be, if you're willing to wait for the data. The other benefit we get from using Splunk is that any staff member can go in, fork any of those dashboards, or start a dashboard from scratch. And because obviously our professional staff, don't know everything about what end users might want or what user specialists might want as information. So we have all those dashboards that keep popping up that gives us ID, and we can reintegrate the stuff in our official monitoring dashboard. So I'll just give you a quick overview of some of the graphs that we're generating and some of the data that we are collecting. So in our Lustre overview dashboard, obviously we wanted to have a general view of the utilization of the different file systems. So how much space are we consuming on those file systems? Are we getting close to having issues with it, both as far as disk space and as far as inodes are concerned. Obviously today inodes are not too much of a big deal on our systems right now, but we've had issues in the past, so we try and be prepared. And we want to keep track of the number of clients connected. So we have close to 200 clients that are down right now that were at the time that I took that snapshot. So So any disparity between the number of connected clients between the file systems will probably indicate an issue with our compute nodes configuration, where maybe somebody pushed the bad configuration and we don't have the file systems mounted everywhere. And of course, we've got the basic views where we will map the, where, as pretty much everybody else here, we're most interested in metadata IOPS, which is the main cause of failures at our site. So we want to keep track of metadata IOPS per file systems and also OSS IOPS, just to get a ballpark of what's going on the system, and should we look into more details at a specific file system. And in the bottom, you'll see the read and write throughput over a period of time also. This graph looks a bit like a mess, but it's surprisingly useful. It's the top clients, the top Lustre clients as far as generating metadata IOPS are concerned. So obviously we cannot look at that and isolate a specific client out of there. But what we want are pattern and mostly clusters of clients doing similar rate of IOPS. So we see a bunch of horizontal lines in there, and kind of a cluster in a spike in the middle on the left also, which is indicative to us of a group of nodes running probably the same job. Often it's a big serial job that started at the same time, or a big MPI job that does synchronized IOs, and that might have an impact on the file systems. So it kind of points us when there are issues on which node we should be looking into to have more details. And obviously with Splunk we can zoom in on parts of that graphic to get more information. So now to file systems specific dashboard. So we wanted to have a view of the utilization of each of our targets for each file systems. So I just saw yesterday that there was something similar in the Intel's package. So basically each bar is the latest status of an OST. The yellow part is the used space, and the red line is the number of files on that OST. And here in that case, you see there's an OST somewhere in the middle that has less space utilized and less files on it. In that case, we had about 2-3 weeks ago, we had an OST that became desynchronized with the quota, and we needed to put it offline. So that's kind of a constant reminder that we need to take action on this one. And any time that we put OSTs offline or that things become desynchronized, we can see it right away in the graphs. In the bottom, you see that the rate of consumptions of our disk space and of our inodes over time. So this one is a bit time consuming to generate, but it's interesting to see the patterns and how the disk utilization is growing over time. So that in that case, it's a 500 terabyte file system. We can see that we're going to hit issues in a couple of weeks, probably. But it's a good indicator to operational staff, if action needs to be taken to purge a file system. In that specific case, we've had a big growth in the last couple of weeks because we're about to reformat one of our older file systems. We've been transferring a lot of data to this one. And this is one of our most interesting, view that we've made. So earlier, a couple of minutes ago, we saw the top clients, top Lustre clients. This is the top Lustre users, basically. So this is a 15 minutes view of the jobs on the cluster. So those are the jobs that were generating the most IO utilization in the past 15 minutes when the snapshot was taken. This one is interesting because, as I said earlier, when we have issues on the file system, it tends to be related to metadata IOPS, and most of the time it's a user's job, running wild and generating like thousands or tens of thousands of IOPS on a given file system. And what will happen in the past is that some users will notice that things will slow down, or his job will slow down, and will create a ticket. User support specialist will look at it, have to get up from his chair, walk to the operational people, and find the right person to find the information for him as to which node were generating the IOPS and which user was running on that job, then the support specialist will go back to his desk, write an email, take action, deal with the user. Nowadays, what he's going to be doing is he looks at that chart and he can dive himself, into find the users that is trashing the file system, kill his job, then write to the user directly, and afterward he goes see the operational people to let them know what has happened, so that we can do a postmortem on the event. So it really frees up time for our operational team, and it kind of empowers the user support specialists into taking action faster. And so just to finish, this is a very small subset of our job report dashboard. So I didn't put any of the CPU load and memory and that kind of information, but I just wanted to pick up the Lustre information. So that's a job that was running on the file system. So basically in the gray part in the middle with the text entries comes from the top of the dashboard. So you just enter the Moab job ID and the name of the cluster on which you want to query the job, and you'll get a report across the time that the job ran for all the utilization for CPU, memory, local drives for that machine, but also all the Lustre file systems that were being used by that job at the time. So here we can see a big spike of IOPS for the beginning of the job, like 4,000, 4,500 IOPS maybe at the beginning of the job, and without much going on as far as read or write throughput is concerned. So it kind of gives us a pattern for the job and allows us to make comparison further down the road if the user has made optimizations or if we have made changes to the system. Also in the bottom left, what you're seeing is the list of software modules that were being used by that job at that point in time. So that gives us the information that, well, this was an MPI job and that's a bioinformatic user doing a genome assembly on the machine. So it kind of put a context around the workload that was going on those machines at that point in time and how they were using the Lustre file systems. So this one today is only being used by our own staff. We haven't been able to export that to end users yet. We're still looking for the good way to do it in a secure way without exposing the information of the other users. But we've used it both ways. So when we notice jobs that make bad use of resources, we will go see the job report to be able to advise the users on how it should improve. And we've had users request that information for us when they notice that their jobs are underperforming. This will also get used when a user asks us to extend his allocation or give him access to run bigger jobs. We can attach that to the email when we answer no to them because they're not making good use of the resources that are already allocated. So the shortcomings of our system that we're currently using, from our point of data. So today we are taking samples every 90 seconds on all the Lustre clients and every 30 seconds on all the servers. Obviously the main issue here is the client. So we generate 1 megabyte of data per client per day, and that's at 90 seconds. Our user support specialist would like us to go down to 15 or 30 seconds. So you can see the big increase here. So it's a couple of gig of data every day that we will need to be able to store. We've also always a bit worried about the impact of running code like that on the compute nodes at the same time as the users are running their job, but we haven't been able to measure an impact on the real code. So we've seen an impact on benchmarks, but we haven't seen an impact on user code yet. And this is a bunch of stats that we collect, but we're not quite sure how to visualize them, like I/O stats for all the drives on our Lustre servers and stuff like that. We're not quite sure how to best visualize them to make the stat useful. So we still collect them, but we haven't been able to make something useful with them yet. And that's it. next couple of steps we want to take with that is we want to look at monitoring the data on the client data on the servers. As I said earlier, it's a bit an issue for us because it will make mapping with the scheduler data a bit more a bit harder. And we'd like to cross-reference our existing stats that we've got in Splunk with the stats that we've got in the Robinhood database. So that's a future project. And so that's about it. Thank you for your time.